Okay, can you hear me now? Okay, great. I'm actually back on my computer because I couldn't figure out an easy way or a quick way to get rid of the pop-up blocker on my husband's computer. But he has actually, meanwhile, installed the classification lab on my computer. So let's see if we can figure that out, and I really apologize for all those delays. So I'm going to share my desktop again. I can do that really well now. Okay. Okay, so, well, here's another version of the CLIA exercise stellar spectrum. So we start out by clicking on File, then clicking on Login, and I usually just use my first initial, but you could enter your first name, your last name, and then click OK. We don't have a table number because we're doing it individually. And have you finished logging in? Yes. Okay. So now that we're logged in, we can click on Run. And the first part of the lab is about classifying the spectra. And then in the second part of the lab, we'll take a couple of spectra and then classify them after we've taken them. So for the most part of the lab, we will use the classify spectra. The first couple of questions, though, on page 17-8 ask about what the grayscale photo looks like of a spectrum. And so we have to go to Preferences. Okay. Maybe I shouldn't have clicked on that, just had my cursor on it. Okay. Oh, well. Let me think. Well, let me see if we can get into the other part of the lab. Okay, so we can get into the other part of the lab. Now, sorry, that's not what I want to do. Let me bring up the window for our chat box again. Do you remember when you didn't have any sound, what you saw there? I went to Preferences and then went to Display and then clicked on the grayscale photo choice. And remember that you saw a light background and individual black narrow lines. This is what the grayscale photo looks like. So the individual gray or black lines will be the absorption lines, and the otherwise light gray or white background is the continuum from the star, which if it weren't a grayscale photo, if it were a color photo, we would see the spectrum of colors. So essentially, every star is like a black body, except for the thin gas on the outer surface of it, where it's cool enough so that you can have atoms that can be excited and absorb photons that come from the inside of the star. So if it weren't for that, gaseous outer layer that is a little bit cooler than the interior, then we would have a perfect black body spectrum, a continuous color spectrum without any absorption lines in it. But because of the cool gases in the outer atmosphere of the sun, those atoms and molecules, depending on the temperature of the star, can absorb photons that pass through from the inside. So by doing that, they remove them from the light that comes in our direction. So that's why the black narrow line is where we don't get any photons or very few, and those would be the absorption lines. And the light uniform background would be the continuum, where we receive a lot of light in all kinds of colors. Okay, so let's go back to the intensity trace, because that is the default setting. I go back to File, and okay, here we can go to Preferences. I'm sorry. Okay. Now, okay, so we can get there. I was just clicking on the wrong part of the menu. Let's see. Unknown spectrum, program list, and let's go to the first start. That's what we were looking at. Okay. I'm sorry. So again, the whitish light gray is the continuum. So the background where we receive a lot of light, and it's, if it were in color, it would be the colors of the rainbow. And the black narrow lines are the absorption lines. So this is where light is absorbed by the cool atoms and molecules in the outer layer. So they remove the photons from the light that is coming towards us. So that's why it's dark at those particular wavelengths. That's characteristic to them. Okay, so this pretty much covers the information for questions 1 and 2. Now, let's switch back to the intensity trace. So Preferences, Display, Intensity Trace. And here we have the intensity values of the curve would correspond to the continuum of colors that we would see. So this is what's called the continuum, and corresponds to the black body part of the spectrum. And the sharp dips, or minima, those would be the absorption lines, because here the intensity drops down, so we get only very few photons at those particular characteristic wavelengths for the atoms and molecules in the outer gas layer of the star. Okay, so this would be question 3. Now we display for question 4 already. We go to the program list and display our first spectrum. That was HD 124320. And it says to choose any point on the continuum. So the continuum was where the intensity was high. And essentially, you can choose any point along the left part or the middle part or more on the right. I mean, you'll probably notice that the continuum on the left is a little bit lower in intensity, and then it increases towards the right. And then, on the right part, it's a little bit lower. I still don't know my left and right. So on the right part, the intensity of the continuum is a little bit lower, and then it increases towards the left, where the wavelengths get shorter. And then at the very left of this particular star, the intensity starts dropping off again. But anyway, any value, any point is fine. You click on it, any point in the continuum of your choosing, and then it displays the wavelength. So this would be 4032, and it also gives you the intensity, which would be 0.93, with a standard intensity of 1 being the largest. So if you would click on a continuum point in the middle, let's say around 4,222.8 angstroms, then you have an intensity of 0.85, which is fine. And even at the longest wavelength end, around 4,440 angstroms, you still have an intensity of 0.79. So those are the kind of values that I'm looking for. So for the continuum, I'm looking for intensity values that are greater than, let's say, 0. In number 5, it says measure the wavelength and intensity of the deepest absorption line on the spectrum HD 124320. Okay, well, we can click on the three deepest ones and just compare what the intensity is if you click on the lowest point. So the deeper one of the left two dips would be 0.29, then the one in the middle, 0.34, and here the rightmost one would also be 0.29. So either one is fine. So you can click back. This one looks deeper because the continual intensity is higher. This one looks shallower, but it's just as low in intensity, but that's because the continuum is also a little bit lower in intensity. Well, let's just click on this one here. So you would put down the 3,969.6 angstrom for the wavelength and the 0.29 for the intensity. Okay, then if you look at the wavelength numbers on the leftmost, where the short wavelengths are, it's 3,900 angstroms, and then the wavelength increases across the bottom to the right to the longest wavelength that is shown, which is 4,500. Now, if you remember, what color, first of all, do you see all the colors of the rainbow here between 3,900 angstroms and 4,500 angstroms? Or if you remember back, what is the wavelength of red light? Let me switch back to our chat window. Welcome to talk. Does anybody remember the wavelength of red light? Well, yes, sure. Well, actually, red light has the longer wavelength. So it would, yeah, no problem. So blue has the short wavelength and red has the longer wavelength. And blue is in the 4,000s of angstroms and red would actually be in the 6,000s of angstroms. But the longest wavelength on our scale here is 4,500 angstroms. So that's still in the 4,000s. In other words, if we were to look at this section of the spectrum in color, then which color would we see? Okay, yeah, blue is coming to you and red is going away from you. That is for the Doppler shift. Exactly. So in this case, we're not looking at the Doppler shift of the star. We're just, looking at the entire spectrum of the star. And these are actually stars that are closer by, so the Doppler shift wouldn't be as drastic. Well, the wavelengths are all in the 4,000s, and we don't have anything longer than 4,500. So you would still see all these colors in here as blue. Maybe a little bit teal at one end, going to purple on the short wavelength end. But yeah, you wouldn't see any yellows or greens or reds or oranges. So this would be for number 6. Okay, then we're going to open another window, and this is the Atlas of Standard Spectra. Now for question 7, and the good thing is you can move these windows around on your screen. Oh, okay, main sequence. Yeah, I need to make a choice here. Yes, these are all main sequence stars we're looking at. So the default, we're clicking on the default, the main sequence standard spectrum. Okay. Well, now you just list in question 7 what spectral types are in the atlas from hottest to coolest. So O, well, the sequence is O, B, A, F, G, K, M, with O being the hottest and M being the coolest. But we also have some subtypes represented. So you want to put down, the entire list. So O5, B0, B6, A1, and then go all the way to the bottom, A5, F0, and so on. And the coolest type would actually be in M5. Now, you don't have to worry about the Roman numeral 5 that's at the end of all these spectral types. That just indicates the luminosity class that we're looking at main sequence stars. So giants and subgiants and supergiants, they would have other luminosity classes. For example, a supergiant would have a luminosity class of 1, a Roman numeral 1. A red giant, Roman numeral 2, and so on. But we're only looking at main sequence stars, so they all will have this Roman numeral 5 at the end. So you can just leave that off. Okay, so after listing all the spectral types, in question 7, it asks in question 8, based on what you learned it's on the next page, 17-10, based on what you learned by scrolling through the standard spectra in the atlas, which spectral type is the hottest? Explain your answer. And just before this question, the lab manual showed you Wien's law. And if you remember Wien's law, that essentially related the peak wavelength, or if you look at a blackbody spectrum, so the wavelength of peak energy output is inversely proportional to the temperature of the black body, or to the surface temperature of the black body. So that means the longer the wavelength of the peak energy output, so we look at the continuum and then look at what wavelength is the highest intensity of the continuum visible. That would be the peak energy output, and if that's towards the longer wavelength, then the temperature would be lower, and we're looking at a cooler star. But if the energy of the wavelength of peak energy output is towards the shorter wavelength end, then we look at a higher temperature star. And you can see this since we're in our atlas, we're at the low temperature end of the spectral type. And well, first of all, you can see that the intensity overall is very low. And then you can see that the intensity actually of the continuum increases towards the longer wavelength. So that indicates, okay, we're looking at a cooler star here. And if we scroll up through the spectral types, let me just click up here. Here we have M0. Here we're getting into K. You can see that the peak energy output is actually starting to come up into the long wavelength end of the spectrum. So, yeah, see here at the shorter end of the wavelength, the intensity is starting to get higher and higher, even though in K it's still lower than the long wavelength. Yeah, then G, you can see now it's starting to come up to be even. Here, G0, it's almost even. See, then F, between F5 and F0, see here you can see in F0, this is getting hot enough so that the intensity is starting to come down a little bit on the long wavelength end. And, it's definitely, the peak is moving across towards the shorter wavelength. See, and then I'm flipping into A, and here it's really becoming visible. Now the intensity at the short wavelength end is much higher, and it's definitely dropping off on the long wavelength end, until we all the way at O, where it is extreme. You have low intensities on the long wavelength end, and the peak has moved off to even shorter wavelengths than the section we're looking at. Okay, so this is how you can tell based on scrolling through the spectra. We can also do it quickly, then it's sort of like a flip book. So you can see how the peak moves across, from the hot stars, where it is all the way on the left or even beyond the left, to the very cool stars, where it's even beyond the edge, the right edge here. Okay, so we're looking for the peak, and then look at number 9, look at the shape of the continuum while scrolling through the atlas. At about what spectral type is the peak continuum intensity at 4,200 angstroms? So 4,200 angstroms is located at about the middle of the spectrum along the horizontal axis. Well, instead of looking at the little atlas here on the side, which we can keep open for reference, we can look at the whole intensity and the wavelength scale. So we're looking at the spectral type where the intensity is highest, around 4,200 for the continuum. Okay, so in the uppermost window here, we have the spectral standard of 05. So that's the hottest type on the list. Let me just scroll the main sequence standard back up there. And then in the middle is our unknown spectrum that we want to classify. And then on the bottom is like the next spectrum down for now, which is B0. Now, well, let's keep looking at the top spectrum and bring it down until we see the continuum intensity peak right around the middle. Okay, so we need to bring it down. Basically, we were looking for when the intensity is almost straight all the way across and maybe just drops off a little bit to the left and a little bit to the right. Okay, so we're getting close here. The F0, we were looking at that before. Now if we go to F5, the intensity is already definitely lower on the short wave side than it is on the long wavelength side of the spectrum. So that might be a little bit skewed. But if we look at F0, well, it looks pretty good. So it is probably between F0 and F5, between these two types. Because in F0, you can see, well, the intensity might be a little bit higher over here. If we check 0.97, at 4,200 or 0.96, it's a little bit lower. But if we compare that to F5, we have 0.93 for the shorter wavelength, and then at 4,200, well, I'm going to pick this thing here. Oops. It would be 0.95, so it would definitely be higher. But then at the longer wavelength, we're also getting something higher. So it looks like it's between F5 and F0. You could make an estimate and give me like an F2 or an F3, or you can just say, well, from the standards that we saw, the F0 was the closest one. Because if we go further down, F5, then you see how the short wavelength intensity is dropping off and the long wavelength is gaining. And if we go back up, F0, it really looks like it's, the most even. It's probably an F2 because, here at F0 we can see that the shorter wavelengths are already picking up a little bit. But again, F0 is fine because that's the closest from the standard spectra. Because if we go up to A, then, it's definitely apparent that the short wavelength side is higher in intensity than the long wavelength side. Okay, let's see, so let's see, look at this, blah, blah, blah. So which spectral type? You put that down for 9, and then use Wien's law to calculate the temperature of the star. Show your work. So Wien's law would be, let me just type that into the chat box. Well, I'm just going to say lambda, because I don't have Greek letters here in my chat box. So the lambda max is equal to 2.9 times 10 to the 7 divided by the temperature of the star. So what we would do, we would actually solve it for the temperature, because that's what we want to calculate. We know that our maximum wavelength is 4,200 angstroms. That's what we are identifying our spectral type for. And solving for the temperature, we can just cross or multiply both sides. Let's do it that way. Multiply both sides by the temperature. That cancels it out on the right side and brings it over to the left. So then we would be at lambda max times T equals 2.9 times 10 to the 7. Okay, so now we have to divide both sides by lambda max. And that cancels the lambda max on the left side. And brings it into the denominator of the right side. So our final formula would be T is equal to 2.9 times 10 to the 7 divided by lambda max. And then our lambda max would be the 4,200 angstroms. You can actually put the 4,200 angstroms into the equation as 4,200. So T would be equal to 2.9 times 10 to the 7 divided by 4,200. And that should give you a temperature, like in the several thousands. Okay, and after doing that, we're finally getting into the task of estimating the spectral type of the 124320, while including the subtype in between the given standard spectrum. Well, in this case, since everyone is working on their own, you can just give me the closest match of the ones that are printed of the standards. I mean, it's up to you if you wanted to estimate any type in between. So I'm accepting if it's in the ballpark, then you'll get points for that particular star. Now, a really useful button here is if you click on the difference button at the bottom right. And now the bottom window, just saw lightning through the window, through my real window in the house. We might get a little bit of weather tonight, so it's tight. Anyways, if you look at the bottom window on the computer, now instead of showing the next lower standard, it shows the difference between the standard spectrum that is shown at the top and the unknown spectrum that is shown in the middle. And you can see if I scroll up and down through the spectral types that the difference gets larger the further I move away from the type that it best matches, and that the difference gets smaller the closer I move to. the type that it matches. So what I want you to do here now is to just go ahead and scroll through the standard spectrum until you find the closest match. So in the case of HD 124320, the closest match would be the A1. And you're supposed to write down what the match is, so that would be A1, and then also give reasons for your answer. And then you can just say, using the difference button or the difference tool in the program, that was the closest match with the smallest difference between the standard and the unknown spectrum. Okay, yeah, let me jump off real quick and bring our dog inside. He might get scared, and I'll be right back. I'm just give me a minute. All right, I'm back on. Okay, so the next question, the line at 3,933 angstroms is caused by, okay, what you want to bring up now is, let's see, the spectral line table. So you go back to File, and then scroll down to the spectral line table. And you can move that over to the left if you want to, or wherever it suits you best. Then if you click on the line at 3,933, so this is 3,900, 10, 20, 30. So the line it looks like it is this short line. Okay, that's 3,932. I click over a little bit. Yeah, so that would be at 3,933. And see what has happened here in the spectral line table. So if I click on the correct dip, or reasonably close, then it'll actually encase the correct spectral line with 2 dashed red lines. But if I click anywhere else, in between, then you just get 1 dashed red line. So if you've nailed it, then you have the correct line encased by the 2 dashed red lines. Okay, so this one would be the calcium 2K line. Now I want you to put down calcium 2K line because there's also a calcium 2H line. It turns out that's the one. Potentially that is very close, so the calcium 2H line is very close to the hydrogen 1 epsilon line. As you can see, the calcium H line is at 3,968, and the hydrogen epsilon line is at 3,970. But for question 12, we were looking at the K line. So that's why it's important that you put down the whole thing. Then number 13, you have classified one spectrum. Now you go through the entire list of unknown spectra and then record your results in the table that is on page 1715. Okay, so you transferred your result for HD 124320, which was the star that we just did. And then for each star that you want to identify now on the list, you go back to unknown spectrum, you click next on list, or, if you wanted to make sure you get the correct one, unknown spectrum program list, and then it lists them in order, and you just click on the next one. That either way is fine. And again, then you go up and down through the standards to see which would be the best fit. So this one looks definitely a lot hotter. So the best fit will be in the O or B types. Okay, yeah, but let's go on. This is basically just more of the same that you're doing right here. I'm not going to require the optional exercise, so you can skip that. So skip number 14. And then you go to number 15. Now we go to the option where we take spectra. Okay, so that means we actually have to go back to our original menu, to the top menu, and go back to Run, and then click on Take Spectra. And what we're getting now is a telescope, well, it's not a real one, it's a simulated one. But it's sort of simulating, okay, it takes a little bit of time to get control of the telescope. Now we're opening the doors of the dome, and we immediately want to turn on the tracking. Because if it tracks, that means the telescope adjusts for the rotation of the Earth, and it moves with the rotation of the Earth. If we didn't turn that on, then we would see the stars go past our telescope because the Earth is turning with the telescope on it. So that's why we need the tracking on. Okay, and so what we want to do now is, let's see, we just click OK, that. Okay, okay, it says here on page 17-12, the third paragraph down, pick any star in the field of view. Well, let's pick a bright one, and we can use the direction buttons, north, south, east, west. Click and hold, and then or we can use a dim star. Doesn't really matter. Yeah, let's use the dim star. And so we see a large red box. This is sort of our finder scope with which we can aim for a particular star. But then in order to take a spectrum, we need to switch to a different instrument, to a spectroscope. So we click on Change View, and here we see the double slit, or the slit opening of our spectroscope. And we just move that until the star is smack in the middle of our slit. We also want to note the right ascension, which would be 6 hours, 12 minutes, and 0.03.04 seconds. So that would go into the right ascension blank of question 15. And the declination, 32 degrees, 47 arc minutes, and 33.8 arc seconds. That goes into the declination blank of question 15. Well, this is basically where it is located in the night sky with respect to all the other stars. Okay, once we have that, so once we have our star in the middle of the two red lines, we click on Take Reading. And then we also have to click on Start to start our count. And it's counting how many photons are coming in. And I think I don't know if the manual will tell us. Yeah, if we go to page 1714, we want to look for the signal to noise ratio, which is on the bottom, and that should be at least 100. Well, we have ways to go with the dim one, haven't we? Well, we could pick a brighter one, and then the signal to noise ratio would move up to 100 a lot quicker, because we would be getting a lot more photons in over a short period of time. Yeah, but just to explain the numbers, here on the upper left, you have object number 431, and then here it gives you the apparent magnitude, and that's going to be an important number. Because the apparent magnitude, that's what you want to put down in the apparent magnitude blank. Well, even though the signal to noise is not at 100 yet, let me just stop the count because this will take a while. Signal to noise just means there's still a lot of random noise, so the curve doesn't look very smooth. It looks very, spiky and edgy and jittery. If we would wait until we get to a signal to noise ratio of 100 or higher, the curve would look a lot smoother. So if you do the brighter stars, then you would get a lot smoother looking curve a lot quicker, because your signal to noise ratio will go above 100 a lot quicker. And of course, if the signal to noise ratio is still fairly low, then you might also, the accuracy of nailing those tips would also be a little bit iffy. But anyway, our magnitude does not change much with the signal to noise ratio. So that was 11.82 for this particular object. So each of the stars is a different object, and they will have a slightly different apparent magnitude, and of course a different spectrum. Okay, if we were to go with this now, you would click on Save, then enter the object number, which is 431, click OK, and then the program tells you the spectrum will be saved in file, whatever name you logged in with, 431.csp. Okay, so then you click on OK, and let's see. If we go to question 16, that's where you put down the file name that it was saved under. And then for number 17, we return to the telescope window. So let's close the Take Spectra window. Okay, and close this window here. Wait a minute. No, let's just go to File. Go back to Run, because if we had closed that window, I think it would have asked if we wanted to leave the whole program. Oh, wait a minute. Okay, I'm sorry. We still want to take another spectrum. Okay, so before we start classifying, you wanted to take another spectrum. So we want to stay in the telescope, change our view again. So that's now for number 17, and then aim our telescope at another star. So if your first star was on the dim side, then take a brighter star as your second star. If your first star was on the bright side, then use a dimmer star for your second star. So once you've centered the telescope with the square, the red square on a brighter star, click on Change View, and then move the spectroscope until you have that star centered in between your lines. Then you take the reading, so you start the count. You can see this one immediately, it's so bright, we'll get up to above 100 before I'm finished speaking. But note the object number 246, the apparent magnitude number 7.34. From this screen, you can also copy down the right ascension, 6 hours, 12 minutes, and some seconds here in the declination, 32 degrees, 59 arc minutes, and some arc seconds here. So we can already stop the count because we're above 135 signal to noise, and you can see how much smoother this curve is. So then, the location of the peaks will be determined much more accurately. And the apparent magnitude is 7.34. And you can see a lower apparent magnitude means we have a brighter star. Okay, then you save it and enter the object number. Click OK. Here's the name. Spectrum will be saved in file, and then you write down the file name for the second spectrum. Click OK. Now we're done with the telescope. So we exit out of the taking spectrum window. And in our main screen, we return to File, Run, Classify Spectra. But of course now, instead of classifying the spectra in the table, we want to bring in the saved spectra. So we go to Unknown Spectrum, Saved Spectra, and well, let's do the dimmer one that we did before. Click on OK. Of course, it's a little bit noisy. And then again, we go through our standard spectra with the difference button to see where we get the best match. Okay, and it looks right around between K0 and G6. So you would probably estimate, if you wanted to estimate something like, G8 or 9, but I'll take either G6 or K0 in an example like that. Okay, so that you would write down into, see if you go to 17-16, that page, you have a data table 3, we have skipped data table 2, so you go to data table 3 and click the enter object name, right ascension declination, apparent magnitude, and then the spectral type. So in this case, we would either write K0 or G6, or we would say, well, it's in between those two, and the reason would be because that's the difference was smallest compared with the standard spectrum. So you do that for the two spectra that we have saved, and then we're almost done. Okay, then in question 19, this is our last question. Let me just end the sharing now. See, we should have noted the apparent magnitude, but actually we can just make one up for this particular one. Okay, let's exit out of the program. And I'm going to end the sharing and switch to the whiteboard. Hang on, just got to find the correct window here. Okay. Okay, so the app share session has now ended. And I'm going to switch over to the e-board. See if I can wrap this up in 3 minutes. All right. So we're going to talk about, I'm going to try to type that out. The classification of the Spectra Lab question 19. Okay, here we want to calculate the distance I could just spell correctly, of the two stars we measured, whose spectra we measured. Okay, and the formula we're given is twofold, sort of. So we have capital D for the distance, and that is equal to base 10, and then times an exponent. Let's see, I'm going to move that up a little bit higher, so to indicate that that's the exponent. M, which is lowercase m for the apparent magnitude, minus uppercase M for the absolute magnitude, plus 5. I'm going to close the parenthesis, see if I can draw a straight line. Okay, and under the straight line, we have a 5. I clicked on a button here that I didn't want to click. Okay, here we go. Okay. So what we want to do in this case, we want to calculate the exponent. We want to calculate the exponent first. So that will be the easiest. And then plug it back into this formula and then calculate the distance. So we want to calculate the exponent first. And for example, now I'm just let's say the magnitude of our star, apparent magnitude, was measured to be 7.34. And it will appear in a second. And our star, and we identified this star as a spectral type K0. Let me just change the color of my pen. So now that we have the apparent magnitude M, lowercase m, we also need the absolute magnitude, capital M. So we go to page 1716 and look at Appendix 1. So from page 17-16, Appendix 1, we see that K0 type, spectral type, has an absolute magnitude of 5.9. 5.9. So we can plug that into the formula, so just the exponent. Almost done. Is going to be lowercase m, which was, parentheses open, 7.34 minus uppercase m, which was 5.9, plus 5, parentheses closed, and then divided by 5. Okay, and let me just quickly open the calculator here. Okay, so we had 7.34 minus 5.9 plus 5. That equals 6.44 divided by 5 equals 1.288. I'm just going to round that to 1.29. Okay, so I'm going to write here 1.29. That's our exponent for the base 10. Now, I'm going to switch to pen color again. Okay, now we plug the exponent into the distance. Actually, that's the distance modulus formula, and we get, let me just put that a little bit lower so we have space for the exponent. D is equal to 10, and now I'm going a little bit up, so we get the exponent in here, and then is 1.29. Okay, and of course, well, the calculator that I'm using is just a calculator on my computer, so it doesn't really, I don't know if it does the decadic logarithm. No, it doesn't. So that's going to be for you to calculate. But in general, 10 to the 1 is 10. 10 to the 2 would be 100. So 10 to the 1.29 is a little bit closer to 10 to the 1 than it is to 10 to the 2. So you probably should get something around maybe 30. Well, it's not exactly linear, but yeah, 20 to between 20. Yeah, let's say between 20 and 30 parsecs. So the distance will be automatically in parsecs. You just put a blank here. Okay, that would be your answer for question 19. Okay, and let me save the slide real quick. Okay. Yes, Jennifer, that's a lot to take in. Yeah, this lab has a lot of different steps, looking at a lot of windows. So it's actually great that we did this session and we can post it so that everybody else can also see how the steps are done in order. It's actually the lab itself, once you know how to do it, goes pretty smoothly. You know, people usually get good scores on these labs, but it's just, you know, a lot of different steps and, you know, a little bit tedious. Okay, so if you don't mind, I'd like to sign off now and help get my kids to bed. And let me know by email if you have any questions about any of this as you're starting to work it out. All right, let me stop the archive and sit tight tonight, listen to the radio.